Okay. Is it doing it? No. Hang on. There we go. Yeah, I turned on the I don't know what it's called. The transcription.
It's called closed caption.
Oh, okay. I knew that. Okay. Let me see. My math, I finally got Pearson to talk to me, and Red Shelf is still having issues. So, and that's who we're getting the MyLab through. So it's going to be a little bit before. Once that gets settled, I'll be able to get it up for y'all. But because of that, I haven't been able to either get it onto my classes into the courses through Canvas or assign you MyLab. So once that happens, I'll get it on to y'all. I'll send it on to y'all. I'll put it in as I'll post it as an announcement, and also send out an email through Canvas. Yeah. Oh, that's what I need to do. And right now I'm setting up my cameras so we can have class. Finding my PowerPoint again. Oh, geez. Oh, that's the wrong file. That's why. Oh, and I haven't posted the PowerPoints in Canvas yet. I'll get the PowerPoints into Canvas today. I meant to get it done today, this afternoon, but I got sidetracked. Oh, come on. Some days PowerPoint takes forever to load up, and other days it just boom, there it is. Finally, I'm trying to remember where we ended. Does anybody remember where we had ended?
We were calculating the angle of when
Yeah, I
things go
remember now.
over. Yeah.
Let me see. It was have we done the converting radians to degrees and vice versa?
No, sir.
That's what we're doing today, I believe.
Okay. Radians and degrees. There it is. It's not always fun teaching two or more sections of the same class because we always end up at a different point in those two classes. Where to Zoom? Where'd it go? There it is. Yeah. Let me. Well, my camera's gone. There it is. Here we go. I gotta move this over here. I'm gonna resize this. There we go. So this was the slide we ended on. I don't have my chat up. Yeah, and this class has, I think it has 14, maybe 13 students in it. Technically, there's not enough people to make, but they let me have this class. So yeah, I think everybody's here. Okay, and what time is it? Oh, it's 2 minutes after. So I need to. Yeah, I turn my phone into a clock, so I can see what time it is. All right, and oh. There we go. Okay. So right now I need to drop this. All right. Yeah. I like y'all to have your videos on so I can see your pretty faces, and pin my screen so that way my camera view, my shared view, and me over here is all you really see. And then put your full name in the chat for attendance purposes. And if you don't sign in, I don't know you were here and I can't count you as present. What's next? Oh, all right. So right now I need to get rid of that and pull this up. I have put something in files. Let me get out of this for a second. And hopefully we'll get to that today. What I put in files is this set of worksheets. There are 2 pages to this. And so we'll be looking at this later. We should get it to today. And so right now, we're going to talk about what it means to be converting from radians to degrees. All right. When you have a circle, right, 1 complete revolution is 360 degrees. So 1 complete revolution in radians is 2 pi. So 300 radians. I always forget that part. So 360 degrees equals 2 pi radians. So if I wanted to look at half a circle, so I'm only going this far, it's like a Pokeball, doesn't it? This is 180 degrees. So, and that's half the circle, so that's going to be pi. So 180 degrees equals pi radians. In most of mathematics, we talk about angles and stuff like this in terms of pi. We don't typically use degrees. We use the radians. So if the angle measure is a decimal number, like 2.37, then that's in radians, and that's over 90 degrees and less than 180 degrees. It's less than pi. Pi is 3.1415, and whatever that number is. So 2.7 is going to be less than that. So that's what we're talking about here with this. So we have different things to talk about. So pi radians and 180 degrees, if I divide, so we have 180 equals pi. So if I divide by the 180, so that would leave 1 degree on this side. And I divide pi by 180, and that's still in radians. That's how I get this first fraction here. So that gives us 1 degree is pi over 180. So every 1 degree, if I multiply it by pi over 180, then that gives me the number of radians. This fraction here, well, let me talk about the other one as well. This one it's done the same way, but instead of dividing by 180, we divide by pi. So we get 180 degrees divided by pi, so that's 180 over pi degrees is the same as 1 radian, because pi over pi is 1. Okay, so 1 radian is 180 over pi degrees. These two fractions, because the numerator and denominator are in different units, but they measure the same amount, 180 degrees and pi radians is the same distance. It's the same angle. So it's like dividing something by itself. So this is what we call a unit fraction. And in mathematics, and those of you who took chemistry dealt with something like this in chemistry, when you're converting from one unit of measure to another unit of measure, you're multiplying by unit fractions. Okay, and so that's what we're doing here. That's what we're going to end up doing. We're going to multiply the number of degrees by pi over 180 to convert it to radians. And that's the first thing they ask us to do here. Oh, wait a second. Okay, so converting these to radians, let me change the page. We have 45 degrees. If I multiply this by pi over 180, and this will be in radians, because I'm putting pi back into the measure. Okay, if I'm putting pi back into the measure, then it's becoming a radian. If I'm dividing pi, I'm taking pi out of the measure and I'm making it degrees, but here I'm making it radians. So we have 45 over 180 pi radians. But I'm not done, because I can reduce this fraction 45 over 180, and there's a reason why I wrote it that way, because I can do that. So does anybody know what this equals? How many 45s are in 180?
Four.
So that's 1/4 pi radians, but we typically write it as pi fourths or pi over 4. I will very often read fractions with pi. I'll write them this way with pi in the numerator, but I'll say the fraction pi. This is 1/4 pi. We'll end up getting pi thirds, but I'll say 1/3 pi. Pi over 2, I'll say it's half a pi or something like that. Or well, that I usually say pi halves. So we could have 3/4 of a pi and 3/2 pi, and those things that happen. Okay, so now 210 degrees, I want to convert that to, well, and technically I have the degrees here on the 180, because now the degrees disappear because one's in the numerator and the other's in the denominator, and that just leaves radians. Same thing happens here. We're going to multiply it by 45. I mean, I was looking at the wrong thing. Pi over 180 degrees radians. All right, the degrees, the symbol for degrees goes away, but now I'm going to reduce the fraction 210 over 180 pi. Now, I was taught this in was it 3rd grade? I believe it was. These zeros I can just ignore, because it's like dividing both numerator and denominator by 10, or I'm factoring out the 10s. So now I have 21 over 18. Well, 3 divides both of those nicely. So 21 becomes 7 and 18 becomes 6. So this is 7/6 pi. Or I will typically write it as 7 pi over 6. So that's just a little bit more than half a circle. Now, remember negative, all right, positive means we go in a counterclockwise direction. So that's a positive degree. Negative degrees go in a clockwise direction. So and so this is going to wind up in the 4th quadrant, where if it was positive, it would wind up in the 1st quadrant. So negative 60 degrees times the pi over 180 gives us a negative 60 over 180 pi. Again, we're in radians. The zeros I can ignore, and then 6 divides both 6 and 18. So my numerator is 1, my denominator is 3. So this is a negative 1/3 pi. The negative sign doesn't go away. I'm getting out of screen. Camera range. Or a negative pi thirds. Either way is correct. We typically write it with the pi in the numerator, but how you say it is just personal preference. The textbook, I think, almost always writes out the word radians, but I tend to abbreviate it. And the 100 is done the same way.
I had a question.
Yes. Go ahead.
When we put down the answer, do we need to put down the entire word radians or just that abbreviation?
I'm cool with the abbreviation. A lot of times you don't even need that. If you have pi, then we're under the understanding that it's in radians. If you write it as a decimal, then you should put the radians, either the abbreviation or the full word, whichever works for you, because I'm not that picky.
Okay.
It's like using M for meters or IN for inches. It's the same concept. All right, so 100 degrees times the pi over 180 gives us radians. And so that's the same as 10 over 18 pi radians. Well, 10 over 18, 2 divides both of those quite nicely. So that gives us 5/9 pi radians, or 5 pi over 9 radians. My typical way of writing it is this way, but you can write it this way. Sometimes I'll write it this way simply because of what's going on in the problem, especially if I'm going to have to divide by pi again, because sometimes that happens. And then the 109, same type of deal, 109 times, it looks like a decimal. Well, let me put this in parentheses. So pi over 180, I went ahead and took away the degree symbols because they're going to disappear anyway. So now we have 109 over 180 pi radians. Now, I believe 109 is a prime number, so I can't reduce that because 180 is not a multiple of 109. The first multiple of 109 would be 218. So for me, this is the answer, or the 109 pi over 180. Now, what the textbook does, they go ahead and multiply it out. They do the 109 times 3.1415 divided by 180 and get this is an approximate answer because pi is irrational. And so if you use a decimal number to represent pi, you're going to get an approximate answer. This is exact. These two are exact answers. So whenever you leave pi in there, you have an exact answer. Where if you divide, put it into the calculator and divide, then you get an approximate answer. So, and they show a little, this is one of the few examples where the textbook goes into a little more detail than I do. So we're always multiplying by 1, so 45 times 1 degree, and so we're gonna use a unit fraction here, which is the pi over 180, and that gives us radians. And it's pi over 4. Let me back up. Oh, went too far. Yeah, they didn't have this step here. They went straight from this to that. And so that's what they're going to do on all of these. They're going to go straight from this to that. And they went to the pi over 4. Because that's how we typically write it. And with the 210, they did the same thing. They did the exact same process. They didn't show the work of reducing the fraction. I expect to see that on any exam I do. And then negative 160, they're going to end up with the negative pi over 3. And then we're on over here. Yes, this one here. So we're at this part now. And so they went ahead and multiplied it out. So they got approximately 1.902 radians. When you round a number, and they didn't ask for this. They didn't ask for a decimal number. Whenever they ask for a decimal number, especially in the homework, they will specify what decimal place. Now in the PowerPoints, a lot of times they don't specify a decimal place. But most times it's 3 decimal places. That seems to be as accurate as we need it to be. A lot of calculations, we go to 3 decimal places. I tell people to the only time you end up rounding the numbers, if you're using a calculator to calculate something, use all the decimal places until you're done, until you get to your final answer. Because if you don't, then what happens is sometimes that last decimal place or the last 2 decimal places might be different because of rounding during your calculating. So I don't like people to do that, because then I have 13 students in this class, I'll get 13 different answers because they rounded at a different place and they rounded differently. Some people rounded to 2 decimal places, some to 1 decimal places, some to 4 decimal places. So yeah, keep all the decimal places until you get to your final answer. And that's when you round, if you are asked to round. As far as I'm concerned, on the tests I give, this is the answer I'd be looking for. Okay. Now to convert the radians to degrees, we're multiplying not by pi over 180, but 180 over pi, because now I want to get the pi, I want to remove the pi. Okay, so the first one is pi force, and I'm going to multiply that by 180 divided by pi. Now and this will give us degrees. I'll put the degree out here. Okay. So they're going to do it the same way that they did the other thing. They did pi over 4 times 1 radians, and then they put in this fraction to convert the radians would be, they'd say radians here, and they would say radians down here, and those would cancel out. I mean, not cancel out, but they'd cross out. They'd knock each other out of the expression, and we're just left with the degrees. And so we have pi divided by pi, which is 1. So this is just 180 divided by 4 degrees, which happens to be 45 degrees. And if you remember, that was the first problem of the converting from degrees to radians. 7 pi over 6 times the 180 over pi will give us the number of degrees. The pi's go to 1. 6 divides 18 quite nicely, so it'll divide that quite nicely and give us 7 times 30, because 6 into 180 is 30, and 7 times 130 is 210. So I was going to write 12. 120. Oh, forgot the degree. You need the unit. You have to tell me the unit. You don't tell me the units, it's minus 1 or 2 points, depending upon how severe I think it should be for that problem.
Sure.
Yes.
Can you do like a walkthrough of that one you just did? Because I don't understand what you do with the 7.
Okay. Well, I'm multiplying by the 7. I have 7 pi over 6, and I'm multiplying by 180 over pi. Another way of doing this is just to write it out. And so you have 7 times 180 times pi being divided by 6 times pi. Does that make sense?
It looks like you're doing the top on the top and then the bottom on the bottom.
Right. Now, these 2 pi's go to 1. So the pi is gone. Now, I know 6 can divide 180. So I divide 6 by 180 by 6. But I'm still multiplying by the 7. This is still in degrees. I'm still multiplying by the 7. So 7 times 30. Because 180 divided by 6 is 30. Now, in a calculator, you can divide the 7 times 180 and then divide by 6, and you'll get the 210. But since when I'm doing these types of calculations, I very seldom use a calculator. So I multiply it out. I'll do it all that way. 180 can be written as 6 times 30. So I have 7 times 6 times 30 divided by 6. So these go to 1. I mean, it's taking numbers apart and putting them back together again in new and interesting ways.
Okay. I understand now. It's just like you just said, doing it interesting ways, because I could have just done it straight across, like 7 times 180 divided by 6, and I would come
Right.
out with 210. But like you said, there's
Yeah, you type into the calculator 7 times 180 and then divide by the 6. And if you're using a calculator, boom, go for it. I don't prohibit you from using calculators to do these problems.
okay. I was just yeah, I didn't know how you got there, but now I know exactly how you got there, and now you showed me another way to do it. So thank you, sir.
Okay. That's what I'm here for. All right. And that was what? That was B. And so now we have a negative pi over 3, and we're going to multiply that by 180 over pi. Right away, the pi's go to 1. And so that leaves me a negative 180. All that's left is 180 in the numerator, and all that's left in the denominator is 3. So 180 divided by 3, and it's going to be negative. Well, 3 and 18 is 6, and so we still have that 10 to worry about. So it ends up being 60 degrees. I forgot the degree symbol. Okay. Now here we have 5 pi over 2. And again, we're going to multiply by 180 over pi, and that will give us degrees. Right away, the pi's go away, and I can divide the 2 into the 180, so the 2 becomes a 1 and the 180 becomes 90. So this is 5 times 90 degrees, which is 450 degrees. All right, it's more than a full circle, which is fine. I think the terminal end winds up at 90 degrees. So it goes a full circle and a 1 1.25 full circles, 1.25 revolutions. Now, letter E is different than what we're dealing with, is 2.5 radians, but we're still going to multiply by the same fraction, 180 divided by pi. Now, this is a case where you're going to type it into the calculator and you're going to get an approximate answer, because what I'm going to end up doing is 2.5 times 180. And then once I get this answer, I'm going to divide it by 3.1415. And if your calculator has a pi button, oh, I got to get the calculator over here. I have tons of calculators. Okay. So here I have this one, and what is it? 2.5. 2.5 times 180. And I'm going to divide by, and where's pi? I have pi right here. I don't know if you can see it. I have pi. It's there it is. It's a little bit, it's in blue, so that means I have to press the second button, and then I hit that. And so now I have 2.5 times 180 divided by pi. All right, the TI calculators do order of operations. So when you're multiplying and dividing, you really don't need parentheses. But if this was addition here, then I would have needed parentheses. There's some calculators that just do it left to right, and they don't worry about the order of operations. Okay, and so this is going to give us approximately 143.239, or I could and it's degrees. But again, if you use 3.1415, you might get a different number than what I got here, because mine didn't round pi to 4 decimal places. It used pi to 8 decimal places, which gives us a more accurate number, which means that it might be, this 9 may not be a 9. All right, so we'll end up seeing what they get. So this was 45 degrees, and this one wound up being 210 degrees. And this one was a negative 60 degrees. And letter E gave us 450 degrees. And letter E, yeah, okay, they rounded to 2 decimal places. So they didn't, so they went 143.24 degrees, which is something to consider doing. Okay. 3.1415 is a little smaller than pi. So this number is probably low, where this one's more accurate. This one's closer to what it is.
Sir, how is the right? We used pi, but you're saying it's a little low, but we used the right, like the specific one.
All right, let me show you. 3.1415. That is not what pi is. That's close to what pi is, but that's not exactly what pi is. So if I press and I enter pi and hit enter, it's 3.14159265254 to 8 decimal places. There's more decimal places to pi than what I have here. So that actually should have been a 6, because that would round up to 6, and then my number would be a little bit high. If I divided by that. Well, let's see what would happen there. 2.4 times 180 divide by 3.1416. What?
I thought you said
Yeah.
2.4. It's 2.5.
Oh, I may have said 2.4, but I typed in 2.5.
Okay, cool.
Okay. Thank you. So this was using the actual pi to 8 decimal places, and this was using pi to 4 decimal places. The numbers are pretty close, but this one is slightly lower than this one.
Wait, so if we don't have a calculator, can we just use pi to the 8th decimal?
Well, if you don't have, if your calculator doesn't have pi, then just use 3.1416. Is it 16? Seems like it should be. I don't know. Okay. So if you're doing this on a test, show me what you're doing in the calculator by writing it down like this. Okay. So like on the previous problem, you would do 5 times 90 divided by, oh, it'd just be 5 times 90, or 5 times 180 divided by 2. Okay, if you show me the calculations you're using in the calculator and you get an incorrect answer, I can kind of figure out what you did, what happened with the calculator use. Okay, because I can usually work backwards. Sometimes with calculators, you have what I call the fat finger syndrome, which is, or the long fingernail syndrome. Instead of hitting a 3, you hit the 6, which is right above it. And if you have a smaller calculator, then you have a smaller work area. And so it's easier to hit the wrong buttons. So that's why it's always a good idea to do the calculations twice. Oh, I know I told you about this calculator. This is a dollar calculator. And it's a scientific calculator. And it's got everything on here that the scientific calculator I typically use. So let's see if this one actually works. Yeah. Well, it comes on anyway. That doesn't guarantee that all the buttons are working. The cover for this disappeared, so it may not work correctly. But anyway, you know, it's just a tiny little calculator. Here it is. Yeah, compared to this one, it's just a small little thing. Okay. Questions? We'll move on. All right, for small angles, arc length is subtended by the central angle and is approximately equal to the length of the chord that is subtended. Does anybody understand what that said?
No, sir. I was just waiting for you to write numbers.
Yeah. So they're using jargon that y'all don't know. All right. So here we have a circle. We have a central angle is an angle that has its vertex on the center of the circle. So this is a central angle. The arc length here is approximately the same distance as the chord. A chord in a circle, a chord connects 2 points on the circle. So that's a chord. Here I have this one here and this one here, and this is a chord. The diameter is a chord where its endpoints are on the opposite ends of the circle, opposite sides of the circle. A chord that passes through the center of a circle is called the diameter. That's the official definition of diameter. Okay. And so this distance here is approximated by this distance here. This is S equals R pi. I mean R theta, where theta is in radians. Okay. So I can approximate this distance by doing this calculation. If I know the radius, if I know the distance, like with this camera, if I know the distance from here to what I'm taking the picture of, then this distance can be approximated by, I have my angle of view. In this case, they're saying our angle of view is 6 degrees 9 minutes. So, which that's actually kind of a small field of view, if you ask me. Of course, is it telephoto lens? Is that what they're saying? Yeah. So the further away you are, the smaller your field of view. And so, how wide is it? I mean, how much can you see? What's the distance you can see within that field of view? How much can I see? What's this distance here is what they're asking basically. So we're going to say R is 725 feet. Actually, we're going to use feet. And theta, they give us theta as being 6 degrees 9 minutes. But I need to convert this degrees to radians because the formula here is in radians. But before I do that, I don't want it in degrees and minutes. I want it in degrees. So I need to convert this number of minutes into degrees. Since it takes 60 minutes to make 1 degree, if I divide the 9 by 60, that will give me a decimal number of degrees. So this divides out nicely, I believe. I got a calculator. I can do that divide. 9 divided by 60 gives us a wonderful little number of 0.15. So I add that to the 6 degrees, so I have 6.15 degrees. And this I want to convert to radians. So it's going to be 6.15 times pi divided by 180. Now, we're not going to want pi in here. I want to, and since it's going to be approximate anyway, I'm going to do 6.15 times 3.14 divided by 180. And to be more accurate, I'd probably use my calculator over here that has the pi built into it. But doing it the way I wrote it here, I have 6.15 times the 3.14. I'm going to go ahead and add the 16. And then I'm going to divide that by 180. Did I do this right? Let me type it in again because I'm not too sure about the number I get. Well, let me go to the next slide because that has a nice picture of what we're dealing about. .15 times 3.1416. Yeah, okay. Okay, I got approximately 0.107 feet, which I think is wrong. We'll see what they got. So they converted it to radians. Or well, they converted the 9 minutes to degrees and then converted that to radians. Okay. Oh, no, I was converting to radians. That's right, not feet. I wasn't finding the distance yet. Okay, so this is radians. So this is what I'm going to use here in this formula. So S equals the radius, which is 725, and I'm going to multiply it by the degrees in radians, which is 0.107, because that is a very small angle. Okay, let me divide this by the 60. No. So we do that multiply, and I'm not going to do it. I'm going to let them do it. My computer.
I can't see. I'm sorry.
What can't you see?
What you're writing, it's like you need to move the camera a little bit.
Oh, there we go. Well, I can see it. Yeah. So we have the radians. Okay. So that ends up being approximately 77.57 feet. And I'd probably round this to either 77.6 or 77.8. I mean 0.6 or 77.58. It just depends upon how many decimal places you want.
Sir, why did the PowerPoint use an approximate number and not the exact number? Because I used the exact number that we ended up with after we did 6.15 times 3.14 divided by 180. I got an exact number. Then I multiplied that times 7.25, and I got a different answer. And it looks like you and the PowerPoint both used the approximate number.
Well, did you get 0.107? What'd you get? So this number is different than what I got, huh? Your number is different than this number?
You know, sir, I
The
don't know how to backtrack on this thing.
the angle.
I got
The-
whatever the exact number is for 6.15 times 3.14 divided by 180, that exact number.
Well, it's an approximate number, but multiplying these, that's what you get. Well, again, this is they rounded this number. So they didn't follow my rule of not rounding until you're done.
Yeah,
They
I'm sorry, I
rounded
used
along the
pi.
way.
Yeah, I used the exact pi. I didn't use 3.14.
Okay. And what'd you get when you multiply by 6.15 and divided by 180? What did you get?
I got a super long number, 0.107 337748996 blah blah blah
Okay.
blah blah.
So they rounded to this and used this.
They're cheating, sir. I see.
Well, yeah, I know. And then when you multiplied your number by 725, what did you get?
Then I get 77.81986.
Oh, wow, that is way different.
Yeah,
mean-
I know.
I mean, that's just, we're talking about 2 or 3 inches though.
Sir, to some people, that's a lot.
Yeah, I know. But again, with this particular problem, we're just approximating the distance, the view distance, which is the distance, where is that? Here. We're just approximating this distance here, which is going to be an approximation no matter how we do it, because that calculation is for the length out here. And this, which is longer than this length in here. So rounding as we're working and getting this shorter distance than this is probably closer. Is that making sense? Because that arc length out here is longer than the chord length in here.
Okay, so then in that case, also your equal signs at the end, they should be little squiggly ones, right? Because they're approximations.
Well, once we set this as the number we're going to use, we use equals. And this should probably be an approximation instead of equals, because I'm betting this also is approximate.
We're not
But
perfect, sir.
in working this type of problem, we don't get real, and I don't get real finicky about, well, I should be using the approximation symbol. Well, sometimes I do, sometimes I don't. So I'm not real picky on that. There are times where you have to be, but that, again, that depends upon your professor and what you're using it for. Again, here we're using approximate numbers to find the approximate length of something. So at the end, we can say that this is 76 feet. That's close enough. Because it's far enough away that half foot difference there isn't going to make a big difference. as far as calculating other things. Now, talking about the area of a sector. Y'all know what a sector is? Again, we go with a central angle, and the central angle marks off a portion of the circle. And in this portion of the circle, we have an area in here, and that's what we talk about, a sector. So a sector is a part of a circle based on a central angle.
Yes, sir. The slice of the pie.
Yeah, it's a slice of the pie. Well, realize you could be like me at Thanksgiving time and get a slice of a pie that is more than half of the pie. Okay, so it's however big the angle is, and so your sector can be small as a very thin slice, which is my mother-in-law always said she wanted, but then she ate off her husband's pie, my father-in-law's pie. Or you could be like me and take over half the pie. But I take it in small segments. But anyway, yeah, we used to do 2 pies every Thanksgiving, and my mother-in-law asked my wife one time, well, why are we buying 2 pies? And I said, well, she said, well, one's for the family and the other's for Thomas. And so, yeah, I love apple pie. I mean, pumpkin pie. I make it from scratch now. I don't buy pies anymore.
Yes, pumpkin, sir. That one's the best. Yes.
Yep. You buy a cooking pumpkin. That's those small, and you get them as orange as you can find, because the oranger they are, the more flavor they have. You scoop out all the seeds and you bake it in the oven for 350 degrees for at least 45 minutes. And then you put that in a blender, and well, you scoop it all out, put that in the blender and mash and mix it all together. And that's what you use to make the pie with, rather than buying whatever at the according to the FDA, or the agricultural people who are in charge of these things, a squash is a squash. So if it says pumpkin on there, it doesn't have to be pumpkin. It could be butternut squash. Butternut squash tastes very, very much like pumpkin. And so 90% of canned pumpkin is actually canned butternut.
That's just weird, sir.
Yeah,
It's really weird.
Ah,
Yeah, I did
that's
not.
that's cheating. Okay. All right. So now back to this. So the area of a sector is 1/2 times the radius squared times theta. This should look an awful lot like the area of a rectangle.
Sir, can't see.
Formula.
Can't see.
But oh, I forgot to move my camera up. Okay. So find the area of a sector of a circle whose radius is 3 is formed by a 45-degree angle. Okay, so as we discovered earlier, 45 degrees is the same as 1/4 pi radians, because in the formula we need to use radians. The radius is 3, so it's going to be 1/2 times 3 squared times pi over 4. And that will give us square meters. They write out the word square meters. I use the abbreviation. So this becomes 3 squared pi divided by 2 times 4. And I wrote it this way to just to show you what's going on. Okay, now this becomes 9 pi 9/8 pi meters squared. Now, if I was to ask a question like this on an exam, this is all I require you to give me. They may require you in MyLab to approximate to so many decimal places. And here they just went to 2 decimal places. Okay. So the area of the sector is approximately 3.53 square meters. Oh, when they say rounded to 2 decimal places, that they're saying it's approximate. Okay. This would be the exact area where they have the approximate area. Okay. Linear speed. Okay, this can be I don't know what to say about it. This is going to be fun. Whoops, hit the wrong button. So we have linear speed. Notice they use the letter V for speed. V in physics stands for velocity. And velocity is what? It's a more common word for velocity.
Acceleration?
Nope. That's a different thing.
Speed.
Speed. Hence linear speed. Dead giveaway. That V stands for speed, and speed is velocity. In physics, you'll see velocity used a lot more than speed. So the velocity is arc length divided by time. That gives you the arc, that gives you its linear speed. Is how much of an arc does it cover in the given amount of time? So if you're told that something has 180 revolutions per minute, then in a minute it revolves around 180 times. So that's its linear speed. Okay. Well, that's so if you talk the distance is whatever. Well, that's not exactly the linear speed. That's how fast it's revolving. And so you can convert that to linear speed based on how far from the center the object is that is revolving. So if you're swinging a rope around, how fast is the tip of the rope spinning? How fast is it traveling? Okay. So angular speed, this is another symbol we use, another Greek letter. It's called omega, and I usually write it like that. It's the angular speed of an object is the angle theta measured in radians swept out divided by the elapsed time. So we have omega equals theta divided by t. Okay. Whoops. Where t is units in time. So that means the velocity is going to equal the radius times omega over time. No, just times omega. Yeah, okay. Why? Well, since S equals R theta, and omega equals theta over t. How did I do that? I'm trying to remember how. I worked it out just the other day and it came to me in a flash. And right now I'm kind of. So that means the velocity is R theta. Yeah, R theta over t, because that's what S is. And theta over t is omega. So that's R omega. So that's how they get this. By doing simple substitution up here with arc length. And then doing substitution again with omega. So omega is measured in radians per unit of time. So how many radians does it travel per unit of time? So that's what we can talk about R theta being. So a child is spinning a rock at the end of a 2-foot rope at the rate of 180 oh, that's where I got 180 from. 180 revolutions per minute. So find the linear speed of the rock when it's released. So at the moment it's released, this rock has velocity going that way. What's this velocity? Well, that's the linear speed of the circular motion. Okay. Trying to figure it. So omega is this value here. So the velocity or the linear speed of the rock is the radius, which is 2 times the 180 revolutions. I can't always spell revolution right. Per minute. Yeah, revolutions per minute is the unit, but we want to convert this 180 revolutions to the number of pi, because we want it in radians, not in revolutions. So 180 revolutions is going around 2 pi. One revolution is 2 pi, so 180, it's doing 2 pi 180 times. So 2 pi times 180, yeah, the revolutions goes away because 2 pi is 1 revolution. And so 360 pi radians. 360 pi radians, yeah. That's per minute is how fast it's going. So the linear speed, we would convert that radians. Oh, no, that gives us omega. And so, does that give the, oh, that's what theta is. 2 pi times the number of revolutions. So that's what omega is. And then we have to multiply by 2 again, because that's the radius. So 2 feet times 360 pi radians per minute gives us 720 pi feet per minute. And so we approximate it by multiplying and rounding to the nearest foot. Yeah, you're gonna see this in the homeworks possibly, but you won't see this on a test. I just find it too confusing. So if it's if it's confusing for me, I'm not going to inflict y'all with it.
Thank you, sir.
Okay. So when they converted the 2,262 feet per minute to miles per hour.
These people are sick, sir.
2262 to 25.7 miles. Yeah. Okay. Now we come to the fun stuff. Okay. Which is a unit circles. All right, unit circles, find the exact and this is in the and there's another one that's similar to this. Where is it? This one, where you and I don't know if I posted this one or not. I can't remember right now. But using either one is okay, because this one, it allows you to put the degrees and the radians and the coordinate points of each of those points in there. But let's go back to this. Okay. So we're going to be able to find the exact values of trig functions using a point on the unit circle. So we're going to first learn about what the unit circle is and what these points are, and then find exact values of trigonometric functions of the quadrantial angles. The quadrantial angles are the 0 degrees and the 90 degrees and the 180 degrees and the 270 degrees. Those are quadrantial angles. Well, and this comes back to 360 degrees. So it all depends upon, are you going full circle or are you just not moving at all? 0 degrees means we don't move at all, where 360 means we did the full circle. Okay. Find the exact values for the trig functions for 45 degrees, 30 degrees, and 60 degrees. And once we find those, we can find the degrees of find the trig functions for the whole circle. and then find exact values. That means we're going to be using calculators. And well, no, exact values of trigonometric for multiples. So doing the multiples means we wind up getting all of these angles in here that are marked in this picture. And we'll discover what those angles are here in a moment. And then use a calculator to approximate the value. So that's where we start using the trig functions here. I have no idea what that is, right? Never had to use it, so. And then use a circle of radius r to evaluate trig functions. All right, the unit circle is a circle whose radius is 1, hence the name unit, and whose center is at the origin. So this would be the origin, where this would be the y-axis and this would be the x-axis. Okay. Any circle of radius 2 has a circumference of 2 pi r, and since the radius here is 1, the circumference of this circle is 2 pi. And so for one revolution around the circle, the arc length is 2 pi units. Okay. And so 180 is half of that distance. So that's half of pi, which is pi, half of 2 pi, which is pi. And then 90 degrees is half of 180. So half of 180 or half a pi is pi halves, or 1/2 pi. If I add a half pi to pi, that gives me 3/2 pi, which is the 270 degrees. Okay. Now they come back to building up the angles on here in just a moment. They start by going this way by talking about trig functions of a real number. Let t be a real number and let p equal xy be a point on the unit circle, that corresponds to t. So they start with sine and say that the sine of t equals y. So the coordinate of this point here is going to be sine. The y value is sine of t. And the cosine of t is going to be x. So this will be cosine of t. Right? When x is not 0, okay, so that means we're not dealing with this point up here, which is 0, 1, or this point down here, which is 0, -1, right? This is a unit circle, so this distance here is 1 unit. This distance here is 1 unit, but it's down below, and so it's 0, -1, where this one is 0, 1. So that means this point over here, the x is negative and the y is positive, so that's -1, 0. So whenever the x is not 0, you can find the tangent of t. The tangent of t is y/x. over X. If you remember from high school geometry and I think do a little bit in algebra 2. Tangent is opposite over adjacent, or sine over cosine. Sine over cosine is y over x. Cosecant, right? Cosecant of t equals 1 over sine of t, which is 1 over y. Secant of t is 1 over cosine of t, which is 1 over x. And cotangent of t is 1 over tangent of t, which is the reciprocal of y over x. So that's going to be x over y. These are the reciprocal trig functions. Yeah, you do secant and cotangent. Okay. Now, if you have a point on this circle that its coordinates are a -1/2, square root of 3/2, then, and it's on the unit circle, so this angle here will have these, you can use these x and y's to figure out these 6 trig functions. So sine is just the y value. So the sine here in this particular situation is square root of 3 over 2. Let me see, how do they do it? Yeah, they say that the x is, I was going to point with my hand. The x is -1/2 and the y is 3/2. So sine is going to be the square root of 3 over 2, because that's the y value. The cosine is going to be a -1/2 because that's the x value. The tangent is going to be, well, it's going to be the square root of 3 over 2 divided by a -1/2. So you're going to get a negative fraction, and it works out to be the negative square root of 3, because the math here tells us that if you break it apart, let me write it down here. You have 1/2 times the square root of 3 divided by a -1/2, right? Because this 3/2 can be rewritten as 1/2 of the square root of 3, which is what I did here. So now this 1/2 and this 1/2, they both go to 1, and I still have a negative sign here. So it's a square root of 3 over -1, which is just the negative square root of 3. So this is the negative square root of 3. And this was what? What did we say this was? -1/2. And now these others over here, I just take these same numbers and I flip the fractions, because now they're the reciprocals. Now the cosecant, I'm going to do some calculating, is the reciprocal of sine. So that's going to be 2 over the square root of 3, but mathematicians don't like square roots in the denominator. So I multiply by 1, because we're always multiplying by 1. I just choose what 1 looks like. So this one is going to look like the square root of 3 over square root of 3, because the square root of 3 times the square root of 3 is 3. So my denominator is 3, and my numerator is 2 times the square root of 3. So that's how I get it. And because they don't show, what they don't show is the method of getting to this. And I just like to think of them as the reciprocals of sine, cosine, and tangent. Secant is the reciprocal of cosine. So the reciprocal of -1/2 is a -2. And the reciprocal, no, the reciprocal of -3, negative square roots of 3 is -1 over the negative square root of 3. I just pulled the negative sign out front. So I'm going to rationalize the denominator the same way I did it down here. I'm going to multiply by the square root of 3 over the square root of 3. So you get the negative square root of 3 over 3. So that's what that one is. Yeah, this is just them doing it this way. Just I don't know. That's 2. If I multiply numerator and denominator by 2, then I get a -1 over the square root of 3, which is what I have here. No, up here. And it works out nice from there. Okay. Next thing. Now, we don't use t when we talk about these angles. We use the Greek letter theta. So this would be the sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, and cotangent of theta. They just use a generic t here to bring us into it, not going to it right away, which is what I would have done. Yeah, theta equals t radians. Okay. Well, then theta is in radians. But we can have theta in radians, or we can have theta in degrees. So the radians and degrees, as long as they're the same angle measure, we're talking about the same thing. So 90 degrees, the sine of 90 degrees is the same as the sine of pi over 2. And so here they want us to find those. Well, we know those points. The points are 0, 1, -1, 0, 0, -1, and 1, 0 over here. So we're talking the 4 cardinal directions. Let me erase this. No, I'm just going to do it from there. So we have 0, 1, which is this point over here. So your x is 1 and your y is 0. So the sine is the y value. So the sine of 0 is 0. The cosine is the x value. So the cosine of 0 is 1. And the tangent is 0 over 1, which is 0. The cosecant, right, when you have measures that have 0 in them, you cannot put that 0 in the denominator. So here I have 1 over 0. Well, that's undefined. So the cosecant of 0 is undefined because 1 over 0 is undefined. Right? Cosecant is 1 over the x value. So 1 over 1 is 1. So the secant of 0 is the same as the secant. I mean, as the secant is the same as the cosine, because the reciprocal of 1 is still 1. And cotangent, okay, is like sine. I wind up with 0 in the denominator. Since y is 0, I'm going to put 0 in the denominator, so that's undefined. All right, they don't even go through the process here, or they do, but they say since the coordinate, the y coordinate of p is 0, so that means cosecant and cotangent of 0 are not defined because you're dividing by 0. So at 90 degrees, now we're going to use 0 and 1. And you end up with the same things, or where sine is 1, cosine is 0, and now tangent is undefined because it's 1 over 0. So they don't even talk about that one. Cosecant is 1 over the y, so that's 1, and they won't talk about secant. And cosecant is x over y, so that's 0 over 1, which is 0.
Or
And so
tangent is 0 over 1.
Which one?
Tangent is 0 over 1.
No, tangent is 1 over z, 0. See, because tangent is y over x. The x is 0, so x winds up in the denominator.
Gotcha. Okay, sorry, I had that reversed. Thank you, sir.
Okay. It's the cotangent that is x over y, so the cotangent in this case is 0. And tangent of pi over 2 and secant of pi over 2 are not defined because the x value is 0, and that's what goes in the denominator for those two. The next one was for 180. So the 180, it looks a lot like the 0 degree, except you're going to have negative values because the x is is negative over here. The sine is 0. The cosine is -1. The tangent is 0 because 0 divided by -1 is still 0. The cosecant is undefined because you end up dividing by 0. The secant, you're dividing 1 by -1, so you get -1. And the cotangent is, what is the cotangent? Oh, the cotangent is the reciprocal of tangent, so 1 over 0 is undefined. So cosecant and cotangent are not defined in this situation. It's only on the cardinal points that you have undefined trig functions. If the angle is anywhere else in here, it won't be undefined. And say, now this one down here is going to be very much like this one up here, except you're going to have negatives. Okay. So sine is the y value, -1. Cosine is the x value, 0. Tangent is -1 over 0, so it doesn't exist. And cosecant is 1 over -1. So that's -1. Oops, I went too fast. Secant is 1 over x, which is undefined. And cotangent is 0 over -1, which is 0, the x over y. Okay. And the for 3/2 pi, tangent and secant are undefined or not defined. And here's a nice little handy dandy little chart that they give you. Okay. Now, finding the exact value, yeah, we're getting close to the end of class. So, 3 pi, the sine of 3 pi. All right, so pi goes to here, 2 pi comes back around. So this is pi, this is 2 pi, and then come back over here, this is 3 pi. Well, 3 pi, the terminal side, is the same as 180. And we went in a positive direction, so it's going to be whatever values we got off of here. So sine of 0 is 0. All right, cosine of -270, well, 270 is going in a counterclockwise direction, but negative means we want to go in a clockwise direction, 270 degrees, which winds up on the 90-degree angle, positive 90. So positive 90 and -270 degrees are going to have the same trig values. So that means this point here works for both 90 and -270. So cosine is the x value. So this is 0. Cosine of a -270 is 0. Yeah, they show going around the circle 1.5 times, and then you wind up back here again. So we're using that point, the same point we used for 180. And for 270, we go in the negative direction, which is clockwise, and we wind up at the same place that 90 degrees does. So we're using the same point, and that gives us 0. All right. Yeah, I always used to go through this part here the same way they're going to go through it. Finding those values there. I think it's a little so we want to find those coordinates, the coordinates for those degrees. Okay, so I have 0 degrees and then 30 degrees and 45 degrees and 60 degrees and 90 degrees. So this is pi over 4. But before we go further, this is the coordinates is 1, 0. And the coordinates here are 0, 1 from what we just did. And now how I build these other coordinates up, there's a trick to it. I don't have to figure it out. Okay. So first thing I do, I make fractions. I put the fraction bar down for the ordered pairs. And it's going to be halves. Each one of these is in halves. So this is the initial setup. Now, I just start counting 1, 2, 3 for the numerators. And then I come over to the other side and I continue counting, but I start over again. I go 1, 2, 3. Now, each of the numerators, I take their square root. The square root of 1 is 1. The square root of 2 is the square root of 2. The square root of 3 is the square root of 3. The square root of 1 is 1. The square root of 2 is the square root of 2. The square root of 3 is the square root of 3. And there I have it. Quick, easy, and simple. About 5 years ago, a professor that I worked with, a good friend of mine over at SAC, showed me this technique or told me about it, and I pondered it, but I didn't use it. And then when I started teaching pre-cal again, I'm using it because it is a lot easier and quicker to find those numbers. Okay. These are the exact values. Plugging it into the calculator gives me an approximate value. So pi over 4, the x value and the y value are the square root of 2 divided by 2 and the square root of 2 divided by 2. So the x and y are the same number. So that means the cosine of the sine of 45 is square root of 2 over 2. The cosine of 45, or pi over 4, is square root of 2 over 2. Tangent is square root of 2 over 2 over the square root of 2 over 2. So a number divided by itself. So that's 1. So the tangent of 45 degrees or pi over 4 is 1. And then we do, so that's, how did they show what that value is? So they went through the deal to find out what those values are. Well, the x and y are the same. So x equals square root of 2 over 2. And that's how they got it. At this point here, you would divide both. So they use the unit, they use the circle of a circumference, the formula for this circle, which is x squared plus y squared. Oh, I'm 3 minutes over. We'll come back to this next time and finish this up then. Yeah, because I'm getting a little into too much detail for us to just quickly run it over. So if you have questions for me for what we've done so far, and this is, I tell you what, this is a lot easier than trying to figure out what those numbers are. Y'all are free to go now. Unless you have questions for me, you can all start. You can, I'm going to stop the share for now.
I have a question.
All right. Thank you, sir. Have a good day.
Thank you, sir. Have a good day.
You too.
Do we have to do anything with the stuff you posted in the files or no?
You can download them. You can print them up. You can use them. They're for you to use.
Okay, just practicing.
Or take notes on.
Okay.
Yeah. Do you used to do your homework with?
Yes, sir. Thank you.
So there are tools for you to use.
Robert's saying, I'm probably going to watch the video again. I'm a little bit lost right now, but I'm going to go back and rewatch the video.
Okay. Email if you're having issues. Y'all can drop into the Zoom. I posted my office hours. Oh, he's gone now.
Gone.
I posted my office hours. So he can come in with either you or the other interpreter.
Sounds good.
Um,
Thank you.
Right. Yes, ma'am.
Sir, did you ever fix the My Math Lab for the homework?
I finally
the-
got an email from the people late yesterday afternoon. And they said that they're still waiting on Red Shelf to fix itself.
So we
So
just use whatever you gave us.
yeah.
So we use.
I'm gonna come up with some worksheets to give y'all so y'all have something to at least to be able to do some of this stuff with. So you'll be able to practice it, and you won't have to be struggling with it.
Okay,
Okay.
thank you.
All right.
Bye-bye.
Bye-bye.